Here's another convergence or divergence question, and it may not look like it, but this is an alternating series, and I like to include this because sometimes you come across problems maybe in a textbook you're practicing on these, and the author's trying to be tricky, and they'll use this cosine of n pi thing or cosine of pi n. What is that really? Let's take a look at what that is. Uh, Basically, it's the sequence cosine of 0, cosine of pi, cosine of 2 pi, cosine of 3 pi. We're describing the sequence of cosine of n pi here from n equals 0 to infinity, cosine of 4 pi, dot, dot, dot. And what do these numbers evaluate to? Well, that's a 1, that's negative 1, that's 1, that's negative 1, that's 1. I guess it'd be a negative 1 next. Yeah, this is just a really silly way of using the sequence negative 1 to the n from n equals 0 to infinity. So, gosh, if you ever see this sort of series, first thing you should do is rewrite it like a normal person would write it. Negative 1 to the n times, and then the rest of the stuff will come on down. Okay, so now that we've got that little technicality out of the way, we still need to figure out whether this series converges or diverges, and whether it's, first of all, we should make sure it is an alternating series the way that we think of it. This would be the AN right here. And what we need to make sure of really quickly is that, yeah, these are all positive, and they are non-increasing. Just take a look at it. These fractions here are getting smaller and smaller as n gets larger. So this is definitely an alternating series. I can use the alternating series test, which says all I need to do is take the limit as n goes to infinity of 3 plus 1 over n squared plus 1. And if I do this, then what do I get? Well, I get 3 plus a 0, and that's a 3. The important thing is that that number is not 0. All right, if it's 0, then yeah, you're great. The series converges. But since the limit is not 0, the series diverges. All right. So that takes care of that problem. One more example. Converge or diverge. This one's more obviously an alternating series. So let's just make sure that these guys right here, are these things positive? Well, they're certainly positive. That's easy to see. And then are they decreasing? That one's a little bit trickier to see, but yes, they are non-increasing. In fact, they are decreasing. And so we do have an alternating series test. If you want to convince yourself of this, you could plug in some numbers. You could prove it algebraically or using derivatives, in fact, but that would take a little bit more work. But if you just plug in the numbers, you'll see you've got 2 over, we'll need to plug in, let's plug in just the perfect squares. Get 2 over something, 3 over something. 4 we can plug in, get 4, the square root of 4 is 2, cubed is 8 plus 3 is 11. The next square would be 9. That'd be 27 plus 3 is 30. And you can check that these are decreasing. The ones that you could plug in, we can get rational numbers from. It's really easy to see that these are decreasing fractions. Anyway, so we have this alternating series test. And the important part of the alternating series test that we need to check is the limit as n goes to infinity of whatever the sequence is once you get rid of the negative bits. And in this case, in order to prove this, you could use L'Hopital's rule by changing it into real numbers. Oh, sorry, these are m's going to infinity here. But factoring is just as well. I could factor out an m from the top and the bottom and cancel. So what that leaves me with is I've got an m to the 1/2 here plus 3 over m. And as m goes to infinity, this is going to go to zip, and this is going to go to infinity. although that's not a number. Basically, we do have 1 over infinity is 0. And that's what we want. We want to see that it equals 0 because therefore, let me spell that correctly for you. Therefore, the series, if it was anything but 0, I would say diverges. But in this case, I can say it converges.